I'm here to introduce the man who probably needs no introduction. I would like to begin by saying sort of a story. Actually, I was chair of the department when Adam applied, and I could just simply say that I thought being chair of this department was a complete disaster for the department, except for one thing. I hired him. So, makes up for all the mistakes I did. When I came in here, and he changed the title to his talk. And the original talk was Rational Approximation to Algebraic Numbers. I was going, this is really, really great, because in senior seminar I talk about algebraic numbers and transcendental numbers. And transcendental numbers, for those of you who will mention have me for senior seminar, are very, very sort of strange creatures. And I thought this would be very, very interesting because this will probably shed some light on transcendental numbers. And I looked at the title and he changed it, and I said, what happened to the original title? And he did change it back. So he's going to talk about algebraic numbers today and rational approximations, so it should be very, very interesting. So I'm going to stop talking right now and introduce the man who needs some introduction, Adam Parker. Round of applause, please.
When you agree to give a title, when you agree to give a talk at a conference, you send something in as a placeholder and then you ignore it and write the talk, and then you show up at the conference and it's kind of 50-50 whether you're actually talking about what you said you were going to talk about. So that's exactly what I did here. Is that's my brother. Wow. I didn't know you were.
Hey, that's my brother.
Whoa! That's so weird. Do we look alike?
Oh.
Who's the older brother?
Oh! Okay, well that was unexpected. That was unexpected. Oh, well, anyway, this is joint work with myself, a colleague from Muskingum named Matt Davis, and a student named Daniel Vargas. And so we're going to kind of talk a little bit of background about the problem. This starts off about a year ago, May 2nd, in 2016. I got an email from a former student of mine here at Wittenberg named Wiley. He was not a math student, not a math major, but he was just a math student that came through like my pre-calc class or something like this. And if you go into my office, there's a picture of the math temple. Well, he was the guy that painted me the math temple as a class for art. Anyway, he asked, how's everything going on in the math temple? The years are just flying past. He says, I can use your help. I have an autistic 7th grade math student named Danny. He rambles on and on about math problems. And there might be some good ideas in there, but basically he's saying he's past what my ability to talk about is. He's kind of exceeded what I'm able to do. This is a 7th grade math in Texas, in Houston. So I write back and I say, so he just starts sending me stuff like this. So he clearly has read something about permutations and combinations. None of those formulas are well, for 2 they're okay, but still, only it should be minus 1. And he just kind of stuff all over the place, probability of a flush, all 5 cards, same suit. So he's just kind of rambling on and on about different things, and just kind of, it's just a hodgepodge of stuff. And so I kind of go through it, and I respond, and I kind of write back about, where his stuff is right and where his stuff is wrong, and I write this nice note back to them, and I hope you find it interesting, keep your interest in math, and I kind of think that's going to be the end of it. It is most definitely not the end of it. He loved your response, I printed it, he rambled on for hours about it, and proceeded to basically send me non-stop emails every day about his math ideas, over and over and over again, just sending me more and more ideas about stuff. So he sends, so he wanted you to see his new work, no idea what it's about, something about disproving limits, which doesn't make a whole lot of sense, but okay, or some hypothesis that's pretty broad, it's about some hypothesis. Take a look and let me know what you think. So anyway, this is what he sent me. He said, okay, this is all that was listed there. And so at least I see a limit, that's good. And so what he says is, if we kind of unravel what's going on here, there's 2 numbers, A0 and B0, and this gives me a way of constructing additional terms of the sequence. So if A0 is 1 and B0 is 1, K is some number that's going to stay fixed, so it doesn't move. So I could compute A2 which is just, or A1, which is A0 plus a constant times B0. And B1 would be a B1 plus A, or B0 plus A0. And so he tells you how he's going to construct these sequences and looking at the limit as they go on and on. And he says that that should approach the square root of whatever number you started with, where C is the ratio of those two values. So he tells me how to define these sequences A sub n and B sub n. He says take the ratio of those, and then take the limit of those ratios, and you should get the square root of whatever number you started with. I didn't really understand what he was saying with that, so I wrote back to Wiley, and he wrote back. He says it's a way to approximate the square root of positive numbers. And k is the number that you're going to take the square root of. And when k equals 2, as n approaches infinity, c will be the positive square root of 2. And so forth. He says that a, b, and c are series. They're not, they're sequences, but we'll forgive 7th grade math teacher. Okay, so this is actually true. Here's our sequences that he said. So when k is equal to 2, I have this n equals 2 right here. The sequences start at 1, and I successively create my sequence. So if I was going to be taking these values for an and bn, I've got this kind of ratio of a sub n over b sub n. And you see that as they're going along, what are they getting closer and closer to? Square root of 2, 1.414. Out here, the differences you can see you're getting, e to the 10, the error is about, 10 to the negative 16th out of 30. And so when I wrote down the numbers and I kind of ran the Excel file, it seems like he's got at least a reasonable thing going on here. I'd actually seen this result one time before in an area of math called number theory. This comes in when we're talking about something called Pell equations. You see this. And so anyway, let's go through the proof. This is a classic result. From 13080. So this is a very classic old result, rediscovered by Danny. So what we do is we take the definition of what we had for A sub n and B sub n and look at how we can define these terms. If I was to do that, it turns out that you get a recurrence relation coming down. And so A sub n plus 1 squared minus 2 B sub n squared is going to be, by the definition of what a sub n plus 1 was, it's going to end up being this. And so if I can continue down by induction, so now I can replace this term by what a sub n, writing it as the previous term of a sub n minus 1, and replacing b sub n with b sub n minus 1, and keep going further back and forth and back and forth. And if I continue to do that, I get an equation that looks like this. What then happens is I divide everything by b sub n squared. So I get a sub n squared over b sub n squared. The b sub n's cancel right here, and I'm left with this right-hand side. Now if we look at b sub n was written as a sub n minus 1 plus b sub n minus 1. And so what's going to happen as n goes off to infinity for just that b sub n? What's going to happen to that term of the sequence? It's going to get larger and larger, right? It's going to get bigger and bigger, which means what happens to the right-hand side? Gets smaller and smaller. And I'm left with a sub n squared over b sub n squared equals 2, or a sub n over b sub n equals root 2, which is what Danny said it was going to be, and what, yeah.
What language was Theon outsmarted doing work in, and did you translate this yourself?
Greek and no. The initial conditions that he had, why choose 1, 1 for the initial conditions? It turns out if we change those initial conditions into different values, it seems to still work. The initial fraction, there's no good reason. Theon, the guy who did it in 180 or whatever, said it is because unity is the principle of all figures and the generator of all numbers. That is nothing but metaphysics. There's no reason to choose 1, 1. You can choose whatever you want. In 1881, so we have the proof of square root of 2 in 180 AD, and in 1700 years later, we have a proof that works for other values of k. And so again, this is exactly what Danny sent to me. We have the initial conditions here. If I want to construct b sub 1 or 2, no, b sub 1, it would be the sum of these two, so what would b sub 1 be equal to? What are those two? 2, exactly right. A sub 0 is 1, b sub 0 is 1. So then I can construct the next term of the sequence and build these up from there. It works very similarly to what had happened before. It requires a little bit of algebra. A sub n plus 1 squared. I would take this and I would square it. I would subtract off, this should be a k for what it's worth, k times that squared. A little bit of algebra gets me here. I continue with that process and I end up with a recurrence relation that gets me to there. Then guess what I do? What did I do before when this was a 2? What am I going to do over here? Divide by b sub n squared, exactly right. I'm going to divide everything by b sub n squared. This will become a sub n over b sub n. This will, that should have been a k, will become k. What do you think happens to the right-hand side? Goes to 0, so I have a sub n squared over b sub n squared equals k, or a sub n over b sub n equals root k. August 12th, so a year later, I get the next statement. I don't know if you can read it there. It says, he says, for every natural number p, and every positive real number k, there is an algorithm of the form a0, a sub n, and he defines his recurrence relations, that can be able to be used to calculate the pth root of k. So I'd written back with the proof of his square root statement, and he says, oh, I can do better. I can actually give you the pth root. So not just the square root, but now I can do the third root, the cube root, the fourth root, any root of this. Now, the way he does it is he again defines sequences of sequences. We have our initial conditions, which he says should all be equal to 1. A sub 0 equals 1. B sub 0 equals 1. C sub 0 equals 1. The a sub n's are always listed there. You can kind of see that every term except for the first one in the a's has this k value. You see that there? And every term except for the first two have k's on the b value. Everything but the first three of the c's have the k value. And so you end up with this kind of triangular thing. You see how the k's are kind of cascading down over in this triangular type of way? While I had seen the square root before, I had not seen the pth root before. This was brand new to me. And so this is another form of that might be a little bit easier to understand or a little bit easier to see. These are the terms of my sequence, and this is a matrix. If I was to multiply this out, I would have 1 times a sub n, k times b sub n, plus k times c sub n, plus k sub d sub n. That is exactly what a sub n plus 1 was supposed to be. And b sub n plus 1 was a sub n plus b sub n, and then the k's take over. Do you see it there? And then 3 without the k's, and the rest being equal to the k's. 4 without the k's, and I end up with this nice little matrix. And the theorem he says is that a sub n over b sub n, which should be equal to the pth root of k. Well, I saw this. I'd never seen this before. I go back to my Excel file. So I'm now having a sub n, b sub n, and c sub n. So I have looking for the cube root. I have a value k of 4, so that's going to be the third root of 4, the cube root of 4. And so I went through, there's my initial conditions across the top, 1, 1, 1. And then I cascade down, I have my a sub n's, which depend upon the terms before it. You can see here, if I was to look at that, it is the term and then k times the b and k times the c. I take the ratios, it's an over bn. The actual value of the cube root of 4 is 1.58, and you can see here that a sub n and b sub n are converging very quickly to the cube root of 4. And similarly for b sub n over c sub n. You can see that that is converging very quickly to, there it is, 10 to the negative 15. So we're getting very close to those values pretty quickly. And you do it for the fourth. These are fourth roots, so this would be like the fourth root of 3. These are the a sub n, b sub n, d sub n, a sub n, b sub n. You can see that again, we're converging very quickly to the actual ones. So it appears this is plausible. And I'd not seen it before, so this was kind of exciting. So having not seen it before, I started looking around, starting to see whether I could find anything about this. And so I went to Worcester, and I gave a little talk, basically this talk up to right now. And I asked, hey, has anybody seen this result before? And no one had. No one had seen this result before. I started looking around, I looked in algorithm books, I looked in number theory books, and I hadn't seen Danny's result before. Once you say, has anybody seen it before, I asked, did anybody prove it? I could prove it for the k=3 case, and I could prove it for any individual case, but I couldn't prove it in general. Every one of my proofs required something about the number of elements that was in it, so I could not prove, I couldn't figure out an inductive method. So a few people wanted to try, and one of the people that did want to try and actually help me out with the proof is Matt Davis of Miss Muskingum. And so Danny's result, it turns out, is a special case of a more general construction. And you guys are the first people besides myself and Matt Davis that have seen this proof. And so I would like to show it to you. I will say it was at this point that I contacted Danny's parents and introduced myself as a totally non-creepy math professor from Ohio that's been emailing your 12-year-old son. Which went about as well as you can imagine. Every time I emailed him, I had Wiley on the email, but the parents were very understanding when I was like, I'd like to publish a paper with your 12-year-old son. So, anyway. So, here we go. We're going to choose an f of x, some polynomial here. Eventually the polynomial here with the a, the b, the c, the d, all of those coefficients are eventually going to be rational, but nothing is special about them being rational. It's just a polynomial that factors so that it has distinct roots. Okay, so I can't have repeated roots in my polynomial. So I take what's called the minimal polynomial. No repeated roots, and everything is distinct. Now we need a little bit of linear algebra. Now if you haven't had linear algebra, that's okay. You'll still be able to follow kind of the heuristic idea of what is going on with this, but we're going to need basically 3 properties of linear algebra. The first one is if I have a matrix A, much like the matrix that I had earlier, the characteristic polynomial is defined to be the determinant of A minus x times the identity. And so I take that matrix A, I then subtract off another matrix with x's down the diagonal. And then I take the determinant of that. That determinant will have x's in it. That'll be a polynomial, and it's called the characteristic polynomial of the matrix. If that didn't follow, that's okay. It's not a big deal, but that is what we call the characteristic polynomial. The roots of the characteristic polynomial have a special name. They are called Eigen Values. Eigen Values, German for something, I don't know. It's usually denoted by a lambda, so the roots of that are denoted by a lambda. And for each eigenvalue, there is also an eigenvector. We'll call it V, so that the matrix times the vector V is stretched by the eigenvalue amount. So matrices can take vectors and they can rotate them around and move them all over the place, but certain vectors don't get rotated, they just get stretched or compressed. Those are called eigenvectors, and the amount that they are stretched is the eigenvalue associated to that. Now, I have my step 1. I started off with a matrix with coefficients A, B, C, D, E, F, on and on and on. I then put them into a matrix that looks like this. A was the coefficient of the x to the n minus 1 term. B was the coefficient of the x to the n minus 2 term. Let's see if we can get back to it. There's the F, and that's the A that I'm talking about, the B that I'm talking about, the C that I'm talking about. I'm going to place that into a matrix in this way. And if I do a little bit of calculation, it turns out that the characteristic polynomial of that matrix is F. Now, if I know the characteristic polynomial, the roots of the characteristic polynomial had a fancy name. What were they called? Eigenvalues. So if I know the roots of my F, I know the eigenvalues of my matrix. And then it also turns out that I know what the eigenvectors look like. And that's only because this is a very special kind of matrix. It's easy to compute the eigenvectors. It's easy to compute the eigenvalues of that because there's so many zeros. And the ones are in very special places. And so that if I'm given that matrix right there, a little bit of computation, if I just work that out, the characteristic polynomial will end up looking like the f, the a, the b, the c will be in the right place. The roots of that will be my eigenvectors, and my eigenvalues will look like the following. And that's like a Christmas miracle. It's just like, you wouldn't expect that to happen, but it did. Step 2. Our goal is to find a sequence that approaches one of the ri's. The ri was the root of the polynomial. It was an eigenvalue of the matrix. And I would like to find a sequence that approaches one of those ri's. Yep. Frosty beverage? What we need to do is that polynomial f had lots of different roots. Maybe one of the roots was 1, and one of the roots was 2, and one of the roots was square root of 2, or something. It had a bunch of roots. What we want to do is we want to take those roots and take the one, special one, and make it bigger than all of the other roots. And so if f had 10 roots, I want to move one of those 10 roots so that it's bigger than all of the other roots. I call that moving it into maximal position. And so if my roots were 1, 2, and 3, I might want to move the root 1 so that it's bigger than the one at 3. And I'll explain how we can do that. But that's the goal of what we want to do. We're going to take a polynomial g that makes that special eigenvalue bigger than all of the other eigenvectors. Values. We're going to make it bigger. So here's what we're going to do. F had a bunch of roots. So f had roots R1, R2, up through Rn. What I want to do is I want to look at that first g1 of x. That first polynomial, k1, is a constant, and then I have x minus r2 times x minus r3 times x minus rn. And I want to look at what that polynomial does. The root r2. 0. Where does it send the root r3? Where does it send the root r4? It sends all of them to 0 except what number? R1. And so I can plug in R1, that won't be 0 because the roots are distinct, that won't be 0 because the roots are distinct, that won't be 0 because the roots are distinct. And so basing what I have here with k, I can send R1 anywhere I like, to a really big number, 10. And it send everything else to 0. I can do the same thing here with G2 and make it look very similar. Constant times x minus r1, x minus r3, x minus rn. What happens when I plug in r1 into G2? 0. What happens when I plug it into r2? Not 0. What about r3? 0, 4, 0. I can now use this to send r2 wherever I'd like. 9 is a perfectly good number. Make it smaller than that, right? Do you see how I'm able to move the roots that were listed up here, r1 through rn? I'm able to move them wherever I would like. In fact, just by taking g to be g1 plus g2 plus g3, this is g1 is the only thing that does anything to r1. All of these are 0 at r1. And so I can move the roots however I'd like. I can make them as big as I would like or as small as I would like. Now, I'm calling g of the eigenvalue, r1, equal to lambda. And I'm calling g of the matrix itself, b. So, r's are the eigenvalues of the A matrix. G is the polynomial that moves things into the right position. And if I plug in the roots for Ri, I get out lambdas. And if I plug in the matrix A, I get out some other matrix B. And it turns out what's nice about the matrix B is that the eigenvalues for the matrix B are the lambda i's. And it turns out that the eigenvectors don't change, which is very nice. So I know everything about B for this. So the eigenvectors don't change, the eigenvalues do. And they're just the image of what we start. All right, this seems like a lot, but we are now pretty much winding down. I write my initial conditions, A0, B0, up to P0. I write them as a combination of the eigenvalue vectors. So they have coefficients alpha 1, alpha 2. I look at the sequence, and this is where that sequence comes from, of A sub n through P sub n is equal to the matrix B raised to a power times the initial conditions. This is how I define my sequence. And we look and see what happens. This is A n, this is the sequence. That's equal to the matrix times the initial conditions. But we just wrote the matrix, or the initial conditions, as a combination of their eigenvectors. I then am going to move things around. What happens with a constant when you have a matrix? What can you do? Pull it out in front, which is exactly what I've done with that alpha 1. Now, the definition of an eigenvector was equal to something times the vector. What was it? Eigenvalue. And so, if I do that successively, that's where this came from. Of V1 will be alpha, or lambda 1 to the n of V1. And then I did it again. This A2 got pulled out in front, lambda 2 to the n V2, on and on. What's also nice, if we look back, I know what V1 looks like. If I go back to it, where are you? There you go. V sub I broke it. V sub I is R sub I to the P, R sub I to the P minus 1, all the way down. And so what I'm going to do is replace, there we go. I'm going to replace V sub 1 with that, but with R1s. I'm going to replace V sub 2 with the same form, but with R sub 2. I'm going to replace V sub P with RP, like that. You see my matrices there? And now what I'm going to do is I'm going to look at A sub n over B sub n. A sub n is the top row. B sub n is the second row. So if I were to do that, the top row will be alpha 1, lambda 1 to the n, R1p plus alpha 2, lambda 2 to the n, R2p plus blah, 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 all along the top. And the second row will be the same, but with p minus 1s. And so all that I've said there, if I have that A sub n, this is just the top row of that over the bottom row. Okay. Now, this is where it gets kind of nice. I have taken one of my eigenvectors and made it bigger than all of the other eigenvalues. I've taken one of my eigenvalues and made it bigger than all of the others. Okay? Now, when I did that, one of these lambdas is going to be bigger than all of the other lambdas. I'm taking everything and I'm raising it to powers, bigger and bigger powers. The lambda that was biggest is going to dominate all of the other ones as I take these to higher and higher powers. And so let's just, for the sake of argument, say that lambda 1 was the biggest eigenvalue that I had. all of this other stuff is going to become inconsequential as n goes off to infinity. And I'm just going to be left with those two terms right there. What's going to happen to the alpha 1s? Cancel. What's going to happen to the lambda 1 to the n over lambda 1 to the n? Cancel. And what's going to happen to r1 to the p over r1 to the p minus 1? It'll just go to r1, which was the root that I wanted to approximate. As n goes off to infinity, the largest eigenvector, let's say lambda 1, will dominate all of the other terms. And so, as that happens, the lambdas, I just divided everything by lambda 1. This is a number less than 1, so as I raise it to powers, it'll go to 0. All of these other ones go to 0, and I have defined a sequence and proven that it's going to converge to the root of that f1, that f that we started with. In summary, let B be a matrix with maximal eigenvector, which we call G of Ri equal to lambda I. We define sequences from that matrix B. I write the initial conditions, and then the limit as n goes off to infinity of A sub n over B sub n will converge to that maximal eigenvalue that we had. Now, what on earth does this have to do with Danny's result? Well, let's see. We're going to start with the function x to the p minus k. That's the f that we're going to start with. If I set that equal to 0 and solve it, I get x to the p equals k, or x is equal to the pth root of k. Except for how many roots are there?
K,
P of them.
Sorry.
That's all right. They all lie in the unit circle in the complex plane, and they are whatever, they're just around. Well, they probably don't look like that because they have to be conjugate. So that's where my roots are. The problem is, how far are each of those roots away from the origin? They're all 1, every single one of them. There is no maximal root. There is no maximal root. They're all of distance 1. But I have a trick for moving things around. And I, in particular, would like to take that root right there, and I would like it to, and it's the real root. That's the real pth root of k. It's on the real number. I want to make it so that that real kth root of p is bigger than all the others. Eventually, this x to the p minus k, the only coefficient which was not equal to 0 was the constant term, so that's what my matrix A is going to look like, which is a nice, easy matrix. I let g of x be equal to that polynomial. And it just so turns out that because all of the coefficients are 1, the real root will get bigger because there can be some cancellation with the complex roots. They won't be as big. You're kind of taking this circle and kind of shifting it in some way, you're kind of shifting it over so that that root does become bigger than all of the other ones. And that is the matrix from Danny's result. So I found a nice matrix A, a nice polynomial, and it just so turns out that in that case, you recovered Danny's result. They converge to that number, which was the pth root of k. What about the title of this talk? Well, if we choose f of x to have rational coefficients or integer coefficients, then the roots have a fancy name. The roots of polynomials with integer coefficients are called algebraic numbers. And so that's the interesting thing. When f has rational or has integer coefficients, the roots of them are called algebraic numbers. And so things like square root of 2 is an algebraic number because it's the root of x squared minus 2. That the pth root of a number is an algebraic number. Other numbers, like Brian was saying, like pi, are not algebraic numbers. Irrational. Well, actually, square root of 2 is irrational too. But this is not an algebraic number. But in the case when I choose f of x to have nice integer coefficients, well then a will have nice integer coefficients. And I can choose g so that it has nice rational integer coefficients, which means that b will have nice rational integer coefficients, which means that the matrix that I use to define my sequence has nice rational coefficients. But they converge to a root of the f of x, which was irrational. And so by choosing the g to be just making sure that it's all got rational numbers and making sure that f does, you get a sequence of irrational numbers that converges to a sequence of rational numbers that converges to these algebraic numbers. A couple of facts. We can choose g to make the maximal eigenvalue lambda I way bigger. Like, don't send it to 10 and 9. Send it to like 1,000,000,000,000 and 0.0001. Because then your sequences converge really, really, really fast. And so that you only have to take it like 2 or 3 terms in your limit before you are getting really good approximations for these irrational numbers. Because the lambda I dominates the other eigenvectors much more quickly. And so because you get to choose g however you want, just choose those k values so that the one eigenvalue you're making maximal is super duper maximal. And it converges super duper quickly. It turns out that the choice of initial conditions, which was due to, what was it? Because it's the unity of all life and matter in Greece or whatever it was, the choice of the eigenvalues doesn't matter, or the choice of the initial conditions doesn't matter. If I have my alpha 1 over alpha 1 and my alpha 2 over alpha 2, what's the only thing that matters? Nothing happens to the alpha 1s. They cancel out and they're not meaningful. Unless, what's one bad thing that can really happen? Yeah, if the coefficient of the maximal eigenvalue is 0, well then you're kind of out of luck. In which case, the sequence converges to the second biggest one. So the only time is if your initial conditions are chosen so that your maximal eigenvalue doesn't has a coefficient of 0. But that's really asking a lot of your initial conditions. So initial conditions really don't matter. You can show that they... if, however, B has multiple eigenvalues of maximal magnitude, then the initial conditions do matter. So that if lambda 1 equals lambda 2, then in the limit I get this. Remember, all of the other things are going to cancel out. All of these other terms will go to 0, and I'm left with this. And so in that case, the alpha 1 and the alpha 2 really do matter. They don't cancel out. Despite what some of my differential equations kids out there will do, will say, oh, I'll just cancel the alpha 1s from over here and the alpha 2s from over there, and they will cancel. You're not allowed to do that, right? You have to be able to pull it all the way out in front to cancel from a numerator and a denominator. And so because there's a plus sign down here and a plus sign in the numerator, you can't cancel those out. And so now, if I have two maximal eigenvalues that are the same order, then you can't cancel those out. And if lambda 1 is equal to negative lambda 2, so that they're still the same size, but they're just one's positive, one's negative, well then it oscillates crazy. It goes bouncing all over the place. Let's see if I've got any more facts up here. Oh, the freedom in choosing G. There are lots of polynomials G that rearrange things. I can send K to 10 or 11 and all over the place. I can do all kinds of stuff. I can make these do all kinds of different things. So the freedom in choosing G gives many different sequences that converge to the desired algebraic number. So if I choose P equals 4 and K equals 6, so I'm taking the 4th root of 6. The original matrix from Danny is this. With the initial conditions of 1, 1, 1, 1, I get these sequences approaching the 4th root of K. However, there's nothing that says that has to be it. If instead of choosing g of x, which was x squared plus x plus 1, I choose this g of x, it still moves the real eigenvector, or real root of the of f. It still moves the real 4th root of 6 into a larger position. But now the matrix looks like this. And then the recurrences look like this. And so they give a different sequence that converges. If I want to change this to x plus 2, I get another sequence that converges. If I want to send it to x to the 5th plus 1, I get another sequence. If I want to change my initial conditions, because they don't really matter, I get another sequence. All of them converging to the 4th root of 6. And all of them being rational. I think that's where I'm going to stop. I think how to do on time, just about right there, 45 minutes. There is, the n equals 2 is called the side and diagonal numbers because it's kind of related to Pythagorean numbers a little bit. But right now, we are still looking at some things to deal with complex numbers. But for the most part, we're pretty confident that everything is set. We're all good for showing that these things converge. We're going to publish a paper with a 12-year-old boy from Houston. At least that's the goal. So thank you very much. I appreciate you guys sitting here.